So we've talked a little bit about how our valence bond theory can be used to create, think about how molecules form, but we are going to expand that now and talk about molecular orbital theory. Now this is slightly more complex. It uses some of the ideas we learned for the valence orbital theory, but it takes these concepts a bit further. So we've talked about the Lewis model and expanded that to VSEPR to predict shapes. And then we talked about the valence bond theory. And so now this is the most sophisticated of the three. And this one is probably what we would consider the most correct, although there are ways in which this valence bond theory and even just the Lewis model and VSEPR work really well to explain what we're seeing. So let's think about what a covalent bond is and how it's different in these three different models. So I really want you to be able to focus on using these and explaining what they are and what they tell you, rather than memorizing how to draw anything out. So remember, you can use your notes. I want you to be able to apply these models and explain what you see using these descriptions. So being able to explain a covalent bond in each of these ways is important. So for the Lewis model, when we talk about a covalent bond, what we're talking about is the actual sharing of electrons, and we represent this with those paired up dots, where the hydrogen has 1 and the fluorine has 7, and now when they're together, they each have fulfilled their octet or the duet in the case of hydrogen. So in the Lewis model, this is how we represent a covalent bond. In the valence bond theory, we show overlapping half-filled atomic and hybrid orbitals. So we have like the 1s orbital and then a 2p orbital that has 1 electron in it. And the overlap here forms that sigma bond. Okay, we also talked about pi bonds for double and triple bonds. With molecular orbital theory, we're talking about electrons being delocalized over the entire molecule in these molecular orbitals. So in other words, the electrons are not just stuck in between these atoms, but rather they have a whole area in which they might exist. And we have two terms that we will use repeatedly: bonding and anti-bonding. So here is a comparison of these two bonding theories. So with molecular orbital theory, we're creating new orbitals that consider electrons delocalized over the entire molecule. So it's not like one electron lives in one place and one electron lives in another. It's delocalized as they're bound in this molecule. So with valence bond theory, we consider them localized between a pair of atoms, whereas molecular orbital, they're throughout. Bonds are created from overlaps of atomic orbitals and hybrid orbitals. And instead of keeping the orbitals the same as we did before in valence bond theory, we're actually going to create new orbitals. So molecular orbitals. And instead of being SPD or SP, SP2, SP3, we're going to call them sigma, sigma star, pi, and pi star. Here we have sigma and pi bonds, but here we have bonding and anti-bonding interactions. So I apologize for the confusing sigma pi here and sigma and pi here. I did not make this up, but it's just kind of a little bit odd. And then with valence bond theory, we're predicting shape based on the regions of electron density, whereas in molecular orbital theory, we're actually predicting the arrangement of the electrons, not the whole molecule itself. And this is much better at explaining resonance, which is where this molecular orbital theory really shines. So if you're planning to go on in organic chemistry, this is one of the core things that you need to understand to be successful in organic chemistry. So in molecular orbital theory, we talk about orbitals combining with either constructive or destructive interference. So This comes from the fact that, remember that electrons are really, really weird and they can behave like waves. So when you add two waves together, you can get your constructive interference, or they can interact in a way that they cancel each other out and you get that destructive interference. And so what we would call this is in phase and out of phase. So this in phase comes from the constructive interference and the out of phase comes from the destructive interference. In phase are what we call bonding, and out of phase are called anti-bonding. And we signify this with a star. So the pi and pi star, the pi star is the out of phase, destructive interference, anti-bonding orbitals, whereas the regular ones are the in phase, constructive interference orbitals. So let's look at the sigma bonding and the anti-bonding for our p orbital. So this is a little illustration. If you go to this website here, it's really interesting. You can see all of these bonds forming, and they have the entire series that you would want to see. So they have the 1s, 1p, or 1s, 2s, 2p, 3s, 3p, all of that. They have all of these sigma and pi bonds, and so you can kind of see what they look like. Just as a caveat, this is electron probability of finding an electron. That has not changed. That's still what the bond is. So here we have our destructive interference and our constructive interference. So we have our sigma, and then we have our sigma star. So for the p orbital pi bonding and anti-bonding, we have our constructive and destructive interference, and we have our pi and pi star. So two s orbitals coming together to make constructive interference, it will look like this, and the destructive interference is like this. So you can we represent it with two colors. This area in the middle, that is the node. That's where you will not find the electron. So let's practice combining atomic orbitals. So here we have our two s orbitals, and they come together. So like you can imagine, this is two hydrogen atoms, and they come close together to interact. You can add their orbitals, and you get this bonding orbital, this sigma, or this anti-bonding orbital, the sigma star. So you're really adding the orbitals together or subtracting them to get these molecular orbitals. The bonding orbital results in a lower potential energy, whereas the anti-bonding results in a higher potential energy. So if we were to show our energy diagram, we're starting with our s orbitals, and when we add them together, the bonding orbital, or the sigma s orbital, is lower energy than the original s orbitals. And these anti-bonding orbitals, or sigma star orbitals, are actually higher energy than our original s orbitals. So here's our molecular orbital theory forming our sigma bonding. And this is what it looks like with valence bond theory. So in valence bond theory, remember, we had half-filled p orbitals, and they came together, and we formed this sigma bond here because of this overlap. In molecular orbital theory, we're literally adding them together. So it's like you take the math behind the wave function and you add those two waves together, and then you get this region in which you would find the electron. Sigma bonding has this region in which you would find the electron, and with the anti-bonding, there's no electron here. So you can see that the electrons are delocalized over both atoms, and for our anti-bonding, they're delocalized outside of each atom. This is unfavorable, and the reason it's unfavorable is because it has the higher potential energy, and since the driving force is energy minimization, if this has the higher potential energy, it is less favorable. So let's look at these. What kind of molecular orbital would result from the overlapping of these? Well, so these are in phase, so they will probably add together. These are, they're not even lined up correctly, so they probably cannot interact, and these are opposite. So let's see what so we get our sigma. So it's two p orbitals, and they get our sigma overlap. So we'll get that nice delocalization over the whole molecule. These are unable to combine because they are perpendicular to each other. So in order for these to combine, just like with waves, they have to be in the same plane. If they're out of plane with each other, they can't interact. And these are, again, they are out of phase, so we get our pi star. Okay. So how might we draw this? Well, it's not that different from drawing our atomic orbitals, but then we have to go one step further. So we start with our electron configuration and draw our atomic orbital diagram for each atom. And it works better if we draw one on the left and one on the right side, and then we'll put the molecular orbital in the middle. And so, and the molecular orbitals will be based on that bonding and anti-bonding. And then what you do is you fill in the electrons from the atomic orbitals, you take them from the atomic ones and put them into the molecular orbitals, and you use the same principles you used before. The Hund's rule to pair up opposite spins, and the Aufbau principle, where you fill the lower energy orbitals first. So here's our example from our hydrogen. So here's our atomic orbital here, and our atomic orbital here, and then our molecular orbital in the middle. Note how the bonding orbital is a lower energy than the atomic orbitals, and the anti-bonding is higher energy. The bonding comes from constructive interference, and the anti-bonding comes from destructive interference, and we indicate the anti-bonding with the star. So you should be able to at least recognize all the features of one of these, and be able to recognize if this whole orbital diagram makes sense. So, for example, you can never have more electrons in your molecular orbitals than you have in your atomic. So you have 2 atomic orbital electrons. That means you have to have 2 molecular orbital electrons. These numbers have to be the same. Let's look at He2. So each helium atom has 2 electrons. And so now then we fill out the molecular orbitals, we have to do 4. 1, 2, 3, 4. So we put 2 in our bonding and 2 in our anti-bonding. But this is really unstable. It's really high energy. It's higher than this. And so there's no benefit for the helium atoms. There's no energy benefit. There's no energy minimization that comes from these 2 binding together. And so this doesn't happen. So the nice thing about the molecular orbital theory is it gives us an explanation as to why certain atoms can form certain bonds. And so it explains the inertness of these noble gases. If they were to form a bond, then the anti-bonding orbital will be full. Since that is energetically unfavorable, it doesn't happen. So let's look at what happens when we start adding more electrons. So with our 1s, we have this constructive interference and destructive interference. With our pi orbitals, these are where our p orbitals come into play. And they look really different, okay? So we have our pi is the lowest, followed by our sigma. And those are both lower than the 2p atomic orbitals. Then the pi star is next, and finally sigma star is the highest energy. So let's look at oxygen as an example. Here's our Lewis theory. It shows that we have a double bond between two atoms, and we have two pairs, two sets of lone pairs on each oxygen. For valence bond theory, we imagine that we have a sigma bond and a pi bond, and then we have lone pairs in these py orbitals. For the molecular orbital theory shown here are two s and two p's. Okay, so the two s's, these get filled first, then our two p's. And we stop here. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 6, 8. So we've taken our atomic orbital electrons and distributed them in order from lowest to highest, and we fill these first, followed by these, and then finally these. Okay, so you just keep filling up the orbitals. So this actually shows us that oxygen has unpaired electrons. So oxygen has this really unique property of being paramagnetic. It can be attracted to a magnet. That means that it has to have unpaired electrons, which we do not see in either Lewis theory or valence bond theory. Here's an image. This is liquid oxygen. It's really cold. And it can be suspended in the air by a magnetic field. Okay, so you can kind of see this if you go here, or actually you can just put this into YouTube and see these videos. It's really interesting. And so what happens is the unpaired electrons allow it to line up and be attracted to the magnetic field. If there were not unpaired electrons, it would be repelled by a magnetic field and it wouldn't just stay there. Okay, so that's kind of what that looks like. So you can see this frog being suspended in water, in liquid water, being suspended in the air, and a little frog being twisting around in there. And that's at this website here. Okay, so this shows the energy, this shows the energy of the molecular orbital diagrams for diatomic molecules. Do not memorize this. This is not important. You don't need to know this. What I want you to see is that there is some variation. Okay, so that there is, you can kind of see that between nitrogen and oxygen, the order of the orbitals changes. You don't need to memorize this at all. Okay, that is not important. What is important is that you can take those atomic orbitals, you can form molecular orbitals, and that you can use molecular orbital theory to explain observations such as we do not see diatomic molecules for the noble gases, and that oxygen is paramagnetic.